Hi, in previous lecture I discussed merge sort. It have two algorithm. One is merge sort algorithm and another is merging algorithm. I also discussed one example for both algorithm. Let's analyze the algorithm. It have three steps. First is divide, next is concur, next is combine. So dividing means here there are 8 elements. We'll divide which element will go to first array and which element will go to second array. So we'll do 8 divided 2 minus 1. 0 to 8 divided 2 minus 1, that will go to first array, means array B. Then 8 divided 2 till n minus 1, that will go to second array. So simply we are finding the middle of this array and we are doing the sub array. So this will take theta of 1 time. Simply we are dividing by 2 minus 1, 0 to n divided 2 minus 1 will go to first array, then n divided 2 to n minus 1 will go to second array, and it will take theta of 1 time. Next is concur. We recursively solve two sub problem, each of size n divided 2, which contribute 2t n divided to the running time. So we'll solve this and we'll solve this. Suppose this is t of n, then this is t of n divided 2, and this is t of n divided 2. Next step is combine. Combine means merging. We have already noted that the merging procedure on an n subarray take theta of n time. So we can say C of merge or merging take theta of n time. As we are comparing n element, so it is theta of n time. Let's write recurrence relation for this. C of n. C of n is number of key comparison, number of element we are doing comparison. C of n equals to 2c n divided 2 plus c merge n. For n greater than 1 and c of 1 equals to 0. If there is just one element, we will not do any comparison. So C of 1 is 0. If there are two elements, then we are doing comparison. So this is the recurrence relation for n greater than 1. N value is 2 and onwards. So C merge n, the number of key comparison performed during merging stage. At each step exactly we do one comparison, and after which total number of element in the two array still needed to be processed is reduced by 1. At each step we'll just do one comparison, and after that the number of comparison will just reduce by 1. In the worst case, neither of the two arrays become empty before the other one contains just one element. Let me take one example. Suppose 1, 3, 5, 7. This is one array and another array is 2, 4, 6, 8. Now I'll compare 1 and 2. 1 is less. Next we'll compare 2 and 3. 2 is less. Next we'll compare 3 and 4. 3 is less. Next we'll compare 4 and 5. 4 is less. Next we'll compare 5 and 6. 5 is less. Next we'll compare 6 and 7. 6 is less. Next we'll compare 7 and 8. So 7 is less. Next we'll just move 8. So it did 7 comparison. There are 4 and 4 element in 2 array. Here 4 element, here 4 element, and total number of comparison is 7. So we can say 4 plus 4 minus 1. The size of first array plus size of second array minus 1 number of comparison we did, and that is our worst case number of comparison. Let's see one example of best case. Two array are given B and C. Now we need to merge and we need to write result in array A. Now here index is I, here index is J. We'll compare 1 with 5. 1 is less, so we'll copy 1 to array A. Next I value will increase, we'll compare 2 with 5. 2 is less. Next I value will increase, we'll compare 3 with 5. 3 is less. Next I value will increase, we'll compare 4 with 5. 4 is less. Next I value will increase. So I value will be equal to size of B. Size of B is what? 4. So when I value equals to size of B, we'll simply copy this content into array A. Means we'll copy 5, 6, 7, 8. So how many comparison we did? We compare 1 with 5, 1 comparison, 2 with 5, 2 comparison, 3 with 5, 3 comparison, 4 with 5, 4 comparison. So we just did 4 comparison. In best case, we'll do number of comparison equivalent to size of B. Suppose size of B is M, size of C is N. In best case, we'll do M comparison, and in worst case we'll do M plus N minus 1 comparison. So number of comparison in best case is N1, and in worst case it is N1 plus N2 minus 1. What is N1? Size of B. N2 size of C. So in best case number of comparison is size of B, and in worst case addition of both sides n1 plus n2 means that is equivalent to n. So in worst case number of comparison is n minus 1. So can say in worst case C of merge n equals to n minus 1, and we already have the recurrence. Let's put this value in the recurrence. We can write C host n equals to 2C host n divide 2 plus n minus 1 for n greater than 1 and C host of 1 equals to 0. C for comparison. Let's write in T format. T of n equals to C if n equals to 1, and T of n equals to 2t n divide 2 plus Cn if n greater than 1. So you can solve this by master theorem. What will be A value? A equals to 2, B equals to 2, and f of n equals to some constant multiplied by n. So we can write n. N power log A base B. What is A? 2. What is B? B is also 2. So log 2 base 2, that is 1. We got n. So both are same. It comes under case 2. Running time will be theta n log n. You can also solve by back substitution or recurrence tree method. Running time for merge sort is theta of n log n. That is in worst case, best case and average case. As in worst case number of comparison is n minus 1, and in best case it is n1, or we can write n divide 2 like this. So whether it is n divide 2 or n minus 1, we can write simply constant multiplied by n. So in all case, best, worst and average running time is theta of n log n, as merging take theta of n. Let's discuss space complexity. Space complexity equals to C plus n. N is size of array plus log n. As we are calling recursively, so we need some stack space. Stack size is log n. We can say space complexity is order of n or theta of n. And merge sort is not in place as it needs extra memory. Not in place means suppose one array is given and we are sorting inside this array, that is in place algorithm like insertion sort, selection sort, bubble sort. Not in place as we are copying the array content into another array. We need some extra memory for copying. So we need some extra memory for the other array. That's why it is not in place as it requires extra memory, but it is stable. Stable means in which sequence it is given, we'll get answer in this same way, and we'll merge it. After merging, we'll get 1, 2, 3, 3, 4, 5. So we'll get first these 3, then we'll get this second 3. Next, two-way merge sort or bottom up merging. If divide part is already done and every array contains just one element, then we can do two-way merge sort or bottom up merging. For this, n should be 2 power k. It can be 2, it can be 4, it can be 8, it can be 16, 32 like this. Let's take one example. Consider every element as single array. Means we have already done the divided part. Now we have 8 array having 8 element. Next we'll do two-way merging. So I'll compare these two, 32, 28. 28 will come first. Next we'll compare 17 and 65. 17 will come first. Next we'll compare 35 with 42. 35 will come first. Next we'll compare 86 and 25. 25 will come first, then 86. So after first pass, we got 28, 31, 17, 65, 35, 42, 25, 86. Now these two in one array, these two in one array, these two in one array, and these two in one array. Means we did one pass. After that every array are sorted and every array contains just two element. Next we'll do second pass. In second pass we'll compare these two array and these two array. Now we'll compare 28 with 17. 17 is less. Next we'll compare 28 with 65. 28 is less. Next we'll compare 31 with 65. 31 is less. Next 65 will come. We are just doing the merging part. Next we will compare these two arrays. So 35, 25, 25 will come. Next 35, 86, 35 is less. So 35 comes. Next we'll compare 42, 86, 42 is less. Next 86 will come. So after second pass we got 17, 28, 31, 65 and 25, 35, 42, 86. Now we have just two array and each array contain 4 elements. Next we will do third pass. We have two arrays of 4 elements each. Let's compare 17 with 25. 17 is less. Next we'll compare 28 with 25. 25 is less. Next we'll compare 28 with 35. 28 is less. Next we'll compare 31 with 35. 31 is less. Next we'll compare 65 with 35. 35 is less. Next we'll compare 65 with 42. 42 is less. Next we'll compare 65 with 86. 65 is less. Next we'll move 86 to array. So after third pass we got 17, 25, 28, 31, 35, 42, 65, 86. We got a single sorted array having 8 elements in increasing order. So how many passes required? Here n equals to 8 and after 3 pass we got the result. So you can say log n base 2. Log 8 base 2 means 3 passes required. And what is time complexity for 2A merge sort or bottom-up merging? So there are n element and we need log n base 2 passes. So time complexity is theta n log n base 2. So time complexity is same. There can be MOA merge sort if we are comparing m elements simultaneously. Here we are comparing 2 elements simultaneously, so two-way merge sort. There can be multi-way merge sort also. There can be three-way merge sort. Suppose we are comparing 3 array. Let this is one array, this is another array, this is another array. If we are comparing first element with second element, also the third element, then that will be three-way merging. There can be 4-way merging, 5-way merging. So how many comparison we are doing? Accordingly, that will be merging. Let's discuss pros and cons of merge sort. First, what are the pros? It works for large size problem. Merge sort work well if array size is large. It works for large size problem. Then second, it also works for linked list. Let's take an example. These are two linked lists. Now we need to do merging in these two linked lists. So first we'll compare 1 with 2. Now 1 is less. Next we'll compare 2 with 3. So 2 is less. So what we'll do, we'll just erase it and we'll add this link to 2. Next we'll compare 3 and 4. 3 is less. So what we'll do, we'll erase this and we'll add this linked list. Next we'll compare 4 with 5. 4 is less. So we'll erase this link and we'll add this link to 4. Next we'll compare 5 and 6. So 5 is less, so we'll add a link from 4 to 5. Next we'll compare 5 and 6. 5 is less, so we'll add a link from 5 to 6. So merge sort is applicable for both array and linked list. Next pros, it is external sorting. It sort in external memory. and it is also stable. Stable means order doesn't change for repeated element. Let's take an example. Suppose 3 8 2 3 7 4, and after sort we'll get 2 3 3 4 7 8. So first this 3 will come, then this 3 will come. So order will not change. Suppose this is for mark, this mark is for person X, this mark is person Y, then X mark will come first, then Y mark will come. Next we'll discuss cons. So it requires extra space, so it is not in place sort. While insertion sort, selection sort and bubble sort are in place sort, but merge sort is not in place sort as it requires extra space. It doesn't sort inside that array, it needs some extra space. Next, no small problem. It worked for large size problem. Insertion sort work better than merge sort for small problem. Also, insertion sort work for linked list. That's why if there is a small size problem, if a array having small size, then we prefer insertion sort over merge sort. Next, recursive. For recursive, we need to call same function repeatedly. Also, we need some stack space. That's why this is a disadvantage. In today's lecture, I discussed merge sort running time, two-way merge sort, and pros and cons of merge sort. So, what is running time of merge sort? Theta of n log n for all best, worst, and average case. I already discussed insertion sort. For insertion sort, running time is theta of n for best case, and for worst case it is theta of n square. For selection sort, it is theta of n square for all best, worst and average case. For bubble sort, it is theta of n square for all best, worst and average case. There is a modified bubble sort. For that, running time is theta of n in best case. But in book, which algorithm is given? For that, running time is theta of n square for all cases. In next lecture, I will discuss some question based on merge sort. If this lecture is helpful for you, please like and subscribe. Thank you.